Okay, today I'm going to make a module that I have wanted for a little while to do sort of interesting music theoretically driven processes, mostly to get more interesting chord motion, harmonic motion into procedural stuff that I build. And modular people have a lot of techniques for doing that. I've been using mostly just little sequences, which are not procedural, obviously, because I sort of handwrite them and they tend not to be very interesting. So what I'm going to build today is a module that can run a Markov chain. And my motivation for doing this is a diagram of boring but acceptable chord changes that I saw once in a video. I don't remember which video, but I'll put a link to the channel by Music Matters. There's a music education YouTube channel. I'll put a link in the comments. So this is the diagram, and you can see that it's a bunch of chords by Roman numeral notation, and the arrows represent transitions. So you say like, and there's the upper diagram is for major keys and the lower is for minor. So in the major one, you can see like if you're on 3, then it suggests that you transition to 6. If you're on 6, then you can sort of choose whether you want to go to 4 or 2, et cetera, until you get to the end when you've made some sort of cadence, and then you can sort of move back to any other point in the diagram. And then the minor one is structured the same way. And so what that is a Markov chain, and where so a Markov chain is basically just a set of states. In this case, the states are the chords. So you have 3, 6, 2, whatever, and then a probabilities that the system will transition from any given state to any other state. So in that major diagram, there's the possibility of transition between 3 and 6. Since there's nowhere else you can go from 3 in that diagram, the probability of transition there is 100%, right? So you will always make that transition. From 6, there's 2 possible transitions, 1 to 4, 1 to 2, and you would figure out what the probabilities there were, and so you could start with just like a basic 50% one way or the other, or you could weight it and say it's like 80% to 4, 20% to 2, or something. So there's a bunch of different ways of coming up with the probabilities. I'm not going to worry too much about that. But once you've got that stuff, then you can execute this sort of state transition, and that can be pretty interesting. So you can do all sorts of stuff with Markov chains. People use them for text generation. They've been used a bunch in procedural music, in all sorts of different places, to generate, melodies, where you have, basically like the probability of jumping to a particular note from any other note, and then you can sort of string those probabilistic choices together into a melody, or as I'm going to use it here in chord transitions. But I'm going to build it as just a sequencer where it's got a trigger input, and every time the trigger fires, it does a state transition based on the probabilities that it's loaded up with, and then the states are just floating point numbers. So actually, you'll be able to use the module that I build to do basically anything you could do with a Markov chain, sort of in the context of this kind of system. So that's what I'm going to build. It's not going to be real complicated. Okay, so let's do what I always do, which is copy and paste the last thing I wrote, because that's how you do boilerplate. Okay, so we're gonna, this doesn't need any of this generics goo. Let's go with Markov. It's gonna have quite a lot of data in there because I have to express what the transitions are and the probabilities and stuff. So I have to think about what that is, but there'll be something there. Don't need that anymore. that. It's going to take a single trigger as its input. It's going to output a single value from the sequence, this Markov sequence, whatever that is. Let's think about what that actually means. Okay, so there's the shell of the thing. So now we need to know, how do I represent that diagram that we saw earlier in code? And so that's the simplest possible thing, is to have something like this. Like, I have a vec of all of my possible transitions, and those would look something like from a state, which say that it's a floating point number. Right? That's not going to work, but imagine that that's what it is. And then from that, there's another vec of possible transitions, and each of those goes to a particular state, has a particular probability. So the structure is gonna look basically like that. That's pretty illegible. So let's actually break that out into some structs. So what do we want? Let's have a struct called Markov states, maybe. And that's going to have a value. So this is what the sequence will actually emit if that state is the active state. And I guess I have nothing else to put there. What I really want is I want a mapping from, so I can basically make this be some sort of index rather than a floating point value. So these represent my states, and then those states have themselves a value that actually gets emitted. And I guess I can do that, like the index can be the position in the array, so that's fine. So then maybe this represents the value, this represents the position in the array. So maybe I actually don't need anything else. Okay, let's run with that. So let's say, just for convenience, since we're using this as an array index, make it usize. Okay, cool. So, and then what else do we need? Actually, we need a couple of more things. So this is our transitions, and we need a current state. That's just going to be an index into that list. And then I'm going to use a Schmidt trigger. Someday I should probably generalize this Schmidt trigger stuff so I can don't have to repeat this code over and over again. But it's so short and convenient to write. I don't know. Okay, so our input is just a signal thing, which is the trigger. So we're gonna go. This is why I should generalize this, because I have to think through what a Schmidt trigger looks like every time I write it, even though I've written it 100 times. If the system is, if the input, so if my trigger is high, and if I am not already triggered, then I trigger and do whatever logic is necessary there, which I'm going to think about in a second. If I'm low, then I untrigger. There's not going to be any additional logic there. Okay. And then my output is going to be an array of these guys, because that's boilerplate that I should clean up. And it's going to be self dot transitions, and then the current index, which is self dot current state lowercase. Okay. Why don't you like that? actually get a thing out of that, which is that. Cool. And I need to turn it into a SIMD thing, because this is running it. Now let's just run a signal rate. So it's actually not going to look like that. It's going to look like this. R equals so build an empty floating point thing. Now we're going to do this for every lane. I do this, I know that there's 8 lanes because that's just guaranteed to be true for this type. But I do this explicit call to the lanes method, which hopefully gets optimized out. I don't know if it's constant. It should be. But I do it because that lets me basically search and replace this value if I decide I want to change my block size, and these will all just work. Whereas if I hard-coded this to 8, then that doesn't work. I could make it a constant or something. That is why that's written that way. Okay, and then this is should be up here. That somewhere, and then the thing I actually return is that R. And here I go R equals R dot replace the current lane with that value. Okay. Still don't like it. Because once again, I'm going to do that. Okay. And now this is going to be. Actually, I only need to do it once, doesn't really matter. So now we're going to extract the current lane from this. So, what is it? Is it extract? Cool. Okay. So now what is my actual? So now that should all just work, but I need to actually change state when I get a trigger. And what does that look like? Okay, so I know what state I'm currently in. And so what I'm going to do is I'm going to look that up. So I'm going to go for my current state, and then the transitions part is actually the second bit. Okay, so now I know what I could do, how I could transition out. So I'm going to make some assumptions here that will make this a little bit fragile, but in the way I'm going to use it, I think it's fine. I'm going to not check the transition is empty. I'm just going to assume that there's always a valid transition. I'm going to assume that the probabilities in the transitions are normalized, which means that they add up to 1, to 100%, right? So when you build this structure, you'll have to think about those things and make sure those guarantees are met. That's fine though. So then what I want to do is I want to draw from that. So I'm going to make myself an RNG. And I'm going to use it's choose weighted, which I may have to look up what the API is there, but let's try. So new state equals positions dot choose weighted. And there's. I guess I could just. I'm only doing this once. I could get out of the. I could use thread RNG directly. That's fine. And then it needs a closure, which takes the state, which is a thing, a target, and a weight, So that's this, you know, this U size index and then this weight per probability, and then turns that into a probability. Like I said, I'm assuming they're normalized. So that's going to give me back some or none, since I'm assuming these are non-empty. I'm just going to unwrap that. So this is panicky, but whatever. And what have I gotten wrong? Did I get it right? Cool. Okay. I guess I remember that API then. Okay, so now I know what my new state is, and I can just set that. So current state equals new state. And probably a reference. Oh, right. I need to actually here, extract the state index from that. Cool. Okay, so I think that works as a way to execute a Markov chain. Now I need to think about how to get the Markov chain into it. So I need a constructor. So impl Markov. So I could try and do a builder, like an add state, add transition, and for a general purpose thing, that's what you'd want. But I'm just gonna take a list of state transitions in and just build directly off of that. So this is gonna be a slice of that type. And then return self. There you go. So build it like and we'll just assume that state 0 is always the right starting point when we start out non-triggered. To copy here, cannot, yeah. Okay. Actually do the right syntax. Cool. Okay, so there's my builder. Since the whole reason I'm building this is for these chord state things, I'm just going to hard code that in for now. Okay, so let me look at this graph and build out these states. So I'm going to it's going to be a vec. Okay, so I'm going to this is I'm realizing there's another piece that I need of like no, never mind, I don't. It's just it's a little weird because I need to represent these guys by index, but I don't know what the I'll just do it. And then obviously you'd want a better way of building these for long-term stuff, but this will be fine for now. So the first chord in my list is I'm going to come back and write the transitions later. The 3, and then the 6, and then the 4, and then the 2, and then the 7, flat 7, which I can't represent, I think, 5, 1. 6, 4, 2, 7, 5, 1. Okay, so those are all of the Roman numeral analyses of the chords that I'm going to use, and they're in my thing, except the flat 7, which I need to, since I don't have, in my quantizer, I don't have a good way of doing chromatic stuff. So let me just go with 7 and see how that sounds like, and then come back to that later. Okay, so for each of these I have some transitions. So for the first one, it only transitions to 6, which is element, the second element, the probability is 100%. Okay. The second element, the 6th chord, can transition to 2. It can go to the 4, which is the third element, with 50% probability, or it can go to the 2, which is the fourth element, also with 50% probability. Okay. And then the 4 has 2 transitions. It can go to the flat 7, which is 0, 1, 2, 3, 4. Yeah, 4, with 50% probability. Or it can go to the 2, which is 0, 1, 2, 3, with 50% probability. 3. Okay. And then the 2 has 2 transitions. It can go to the 7, which is 4 with 50% probability, or the 5, which is 5. Okay. And then the 7 has also 2 probabilities. It can go to the 1, which is like a 6, 50%, and or the 5, which is 5 with 50%. Okay, and the 5 has 1, so it can go to the 1, which is 6 with 100% probability. And then the 1 can go anywhere with equal probability. So 1, 2, 3, 4, 5, 6, 7, 8. So 1 over 8. So it's going to be 0, 8, and we're just going to have a bunch of those. 0, 1, 2, 3, 4. Yeah, somewhere I've gotten off. 0, 1, 2, 3, 4, 5, 6. Oh. Can it transition to itself? I guess it can. Whatever, that's fine. Okay. So 1, 2, 3, 4, 5, 6. No, where did I get 8 from? 7. Okay. Cool. So I believe that represents. Right, I actually need to build the thing. The struct is transitions. Okay. So I believe that represents the graph that I had earlier without the flat 7, which I still don't have a solution for. Okay, so let's make a dynamic version of this. I'm going to call this integer chord Markov. Oops, that's not what that's called. Markov. And then it's cat. Please don't walk on my keyboard. Okay, erase the cat's contribution. Okay. And an extra thingy there. Okay. So now I've got that. And should be able to do a thing here. And let's call this Markov. Okay, so now I'll actually write something. So we're going to have our chords, and that's going to be major chord Markov, and that's going to need a clock. So let's give it a sine clock of every 2 seconds we'll change chords. That seems reasonable. Okay, now I need to quantize that. So pitch is a I gave this a stupid name which I can't remember. What is it called? I was just looking at it. Scale degree major. This is my quantizer that maps from scale degrees, which conveniently are the same as the Roman numerals, to actual frequencies that I can use in my oscillators. So it's going to take in chords. So it's going to be this. The output of this will be the pitch of the root note of the chord. So we'll start with that. So I'm going to have an oscillator, just a sine wave. It's going to be playing that pitch, and then we'll route that to the output. I'm not going to try and make this fancy. I just want to make sure that it makes a sensible sounding sound. Okay, and then let's try and play that. Markov.synth. Okay, what did I do wrong? It is called major chords. And I hear nothing. Why is that? Because I misspelled it. I need to make this fail. That's just confusing. Okay. Anyway, those sound, roughly like chord transitions, sort of boring, but that I think is what I'm going to get out of that Markov chain. So I think like this is one of the simplest possible Markov chains you could build. It doesn't have a lot of interest in it, but it's giving us this sort of like cheat sheet of chord transitions that I had copied down, and that's cool. So I think the next thing I'm going to do is I'm going to sit down and I'm going to try and build a little bit of a piece around this, but that'll be another video. So for now, I'm done.